So we're going to move on to a new topic today, and this topic is the topic of flows. We've seen essentially two distinct paradigms for dealing with algorithm design that both change the way we think about what it means to give an answer to a problem. We've seen randomized strategies that allow you uncertainty in whether the answer is correct or not. And we've seen approximation strategies that allow you to give an answer that's close to the right answer, but not exactly that. The profit for that being that you can usually do something a lot faster than you would have if you had to give the exact answer. Flows are not part of that same story in the sense that they are not a different way to think about the resultant algorithm, they're just a different algorithmic paradigm altogether. And they're sufficiently non-obvious that it's, unlike things like greedy algorithms or dynamic programming where you can, or recursion in general, where you can kind of, if you had to, you would sort of figure out how to design some strategy yourself. Flows are not that natural. And although some of you may have encountered flows before, flows are not even something you typically are exposed to when you first start learning algorithms. And just a quick show of hands, how many of you have heard of flows, max flows, min cuts, things like that before? Can you put your hands higher? It's hard to see. Okay, so a reasonable fraction, but not a large fraction. It is a constant fraction, I think, but like any fraction would be in this class, but it's not a very large fraction of students. And so flows are powerful mainly because they are even more of a black box than some of the other algorithmic techniques that you see. Things like, again, like greedy algorithms and recursion, in the sense that oftentimes you will find that if you take a problem and map it to a flow problem, then that's all you have to do to solve the problem. Then there is a standard algorithm for solving it, and you can just invoke these standard methods, and they work very well. And that gives you surprisingly good answers to many problems that you would otherwise struggle to come up with a solution for. These are problems that don't admit to a recursive solution. They don't admit to a greedy algorithm. They don't seem to work with dynamic programming very well. So it doesn't seem obvious how to solve them. They're very different, of course. But because it flows, you can solve them all using the same basic tool. And so it's a very important tool to have in your arsenal. I wouldn't necessarily call it an advanced tool per se, but again, the way the curriculum works, it tends not to be covered that much in undergrad classes. And so we're going to cover it now. And what flows will also do, so historically, one of the flows are also one of the first examples of problems where you can get exact solutions in polynomial time, and yet it exposes to us some of the deeper concepts of optimization and how you connect to things like linear programming, duality, the idea of integer solutions and fractional solutions. That's what we're going to be talking about a lot later. So while flows has one purpose as a very good algorithmic tool to play with, to have in your arsenal, it's also a gateway to this much larger sort of landscape of optimization starting in linear programming. And flows give you a way to see it in a much more concrete way instead of being more abstract. And so we're going to spend a couple of lectures talking about flows, modifications of the basic flow paradigm, examples of how to use flows for solving problems, and then we're going to slowly segue into how flows are a specific example of linear programming. And then we'll talk more about those kinds of things. Okay? So that's the backdrop for why we're talking about flows now and how it'll lead on to the next part of the course, or flow to the next part of the course. So the original motivation for flows, like with most things in computer science, is violence, namely war, and how to defend the United States against this big Soviet menace in the 50s. And the motivation was, if you have, a lot of war strategizing is about supply lines or disrupting supply lines. If you want to cripple the enemy, and not being a person who understands anything about war myself, I'm just me. But if you want to cripple your enemy, of course you can, just bombard them with your weaponry. But of course, there are other things. An army has to eat, as they say. And they have to have their weapons. They have to supply. So if you can disrupt the supply lines, you can, you may not affect them directly, but eventually they will run out of ammunition and food and other things, and then you can defeat them that way. So a lot of strategy in war deals with things like that, sort of meta thinking about supply lines. Not, if you're running a sort of a campaign yourself and making sure your supply lines are not stretched too thin, so they're not vulnerable, and so on. And so in the 50s, there was a lot of strategizing about the Warsaw Pact countries, the whole Eastern Europe under the control, if you wish, of the Soviet Union and their supply lines, and what would happen if there was a war in Europe, in the European landscape theater. And so there's all these, basically what a bunch of strategists at the army sort of figured out that there were basically different locations and different road networks, and in fact the US road network was built precisely to avoid this kind of problem if there was an attack on the US. How would you disrupt the supply lines in order to make sure that you couldn't get supplies from, say, from Moscow towards the front in Ukraine or Poland? So there was this disruption problem. And there's also the question of, well, how much material can be pushed through, right? So in other words, if you want to push, a certain amount of, a certain number of trucks, certain amount of weapons, certain amount of people, all the way to the front, how quickly could you do it, and how would you do it, and what are the different ways of doing it? All these discussions led to what we're going to see today, which is the problem of flows. And so all flow starts with a graph. It starts with a directed graph, and it starts with a graph that has two special vertices in it. So let me draw a graph here. So this will be a graph that we'll be using over and over again. So one vertex. And all of this is in the notes as usual. It's in the link to the syllabus. Wasn't earlier, but it is now. Okay, these are my vertices of my graph. And these two are going to be special in some way. I'm going to call this S. And I'm going to call this T. Okay. And it's a graph, so it has edges. In this particular form of the graph, and this is not how we've looked at graphs before, we're going to assume these edges are directed. That's actually going to be important. So let's say I have some edges here. Maybe I have an edge here. Maybe I have an edge here. Okay. So all flow problems, and this is important because when later on, when I'm going to show you how to take some other kind of problem and convert it to a flow problem, you're going to want to know what you have to convert it to. And so every flow starts with a directed graph. And it has two special vertices. So two of the vertices are marked as special. One is called the source, called S, and one is called the sink, which we'll call T. And we'll always use this nomenclature. Okay? So this is some kind of graph. It's directed, and it has a source and a sink. So what is a flow? Probably one of the more, I've talked about, supply lines and trucks and people and traffic. So one way to think about this is as a road network. You have a starting point, you have a destination point, you have roads, but these are all one-way roads. Okay. Maybe you're in some part of New York City or in San Francisco where you have lots of one-way roads. And flow then is, you can think of as traffic on the roads. The amount of traffic, the volume of traffic. Another metaphor that works, if you think of these as pipes. And these are all pipes and water is flowing through the pipes. So a flow is a specification. So formally, a flow call it F, is a function from the edge set of the graph to the rails. And it'll actually be integers for the most part, but and it'll be the non-negative rails. So it's an assignment of numbers. That means I put a number on this. So let me see. I can put a number here. So maybe the number here is, I don't know, 5. This is again 5. This is 5. This is 3. This is 2. 1. I'm just going to put a bunch of numbers here. It doesn't really matter. So, say 1. Okay, I put some numbers. So far that's all a flow is. And if that's all a flow were, it would not be particularly interesting. Just a bunch of numbers attached to each edge. What's interesting about a flow is that the numbers have to satisfy certain rules. They can't be arbitrary numbers. In particular, and I'm going to go to the next page now. So again, if you have the graph, don't worry about the numbers because we're going to change that in a second. So, what I want from a flow is that, so the flow has satisfied one property. Two properties, I guess. It's properties of flow. The first I already mentioned, but I'll say it again. The flow on an edge, since it's a function from edges to the reals, you can write it this way, is always, where's it? Okay, it's not. And the second constraint, which we'll call a conservation constraint. One way to think about this is that there are no holes in the roads that are sucking in cars that are and absorbing them. There are no holes in the road underneath which is a car factory that's sticking out cars and shooting them out of the road. Weird things like that are not happening. Or if you have water pipes, there are no leaks and there's no extra thing except at the source and sink. So for any vertex that is not the source of the sink, okay, those two are special. The following must be true, that the sum over all u of the flow going into the vertex should be equal to the sum again over all flow going out of the vertex. Okay? So what goes in must come out, with the exception of the source and the sink. Okay? Yes?
So we are assuming pipes are all good, they don't have any
No leaks.
bumps or something.
Bumps.
As in water cannot stay in the pipe.
That's right, no leaks.
No, not going out, but it can stay in the pipe, right?
No one stops their car. It's a highway system.
Okay.
Yeah. Yes.
Could you read that last equation again?
The sum of all the flows going into a vertex, right? So let me draw it out here. So let's say I have some vertex B. I have some edges coming in. That's the left-hand side of this expression. And I have some edges going out of it. That's the right-hand side of this expression. What I'm saying is all the flow coming in must exactly balance all the flow going out. Right? No absorption, no production. Except at the sources. Yes?
It sounds a lot like Kirchhoff's law in electrical circuits.
Yes.
Although that only applies if your voltage and current aren't like crazy values. Where if they are crazy values, you can actually have an accumulation of stuff at the node for a little while and then.
Right, but there is a conservation law that applies there as well. It's just
Right.
not. It's not literally in terms of the current. The other,
Right.
well, even the current has to split correctly.
Yeah, but you could have some cooling and then it will leave and then cooling again.
If you don't have capacitors, I don't think you can have cooling.
It depends on what kind of circuit you have, but
Yeah.
your
There is
normal-
one project group that is looking at electrical circuits and max flows. Which group is that? One group has got a paper that's dealing with electrical. So there's some interesting work on how to solve max flow problems on modeling this electrical circuit. So the connection is closer than yeah, it is actually quite a close connection. Yes, not here. Okay. All right. So this is the constraint we have on flows, right? And we can now start asking certain questions, interesting questions. So the first thing you can ask is, okay, so what does it mean then? Well, first of all, why do you not have this constraint of source and the sink? The idea here is that the source is allowed to produce some flow. Think of the source as well, the source of your traffic or your water or whatever. The sink is the absorbing end, it's absorbing it out. So things pop in here, they come out there, and you don't lose anything along the way. Right? And because you don't lose anything along the way, you can talk about the value of the flow. There's a notion of the value of the flow that makes sense. Okay? And the value of the flow, so once I have such a flow definition, I can talk about the value. So the value of a flow I'll call it V of f, right, is equal to the amount of flow going out of the source minus the amount of flow going into the source. So I never said that the source can't have edges coming into it. I just said it's a designated vertex. Since I said that for every other vertex in the graph, this number is to be 0, this would be nonsensical if I tried to ask this question for something else. But for the source, I can ask this question because it's not required to have this property. And so I can say this is the value. So this is going, out minus in, right? The net flow coming out of the source. And if you think about this for a second, and you can work out the algebra to do this, it's not hard, but the same thing should hold at the sink in reverse order, right? This must also be equal to the amount of flow going into the sink minus the amount of flow going out of the sink. Intuitively, this should make sense. If you push in a certain amount of flow at the source, you never lose any of it anywhere. The only place you can lose it is at the sink, and these numbers should balance. You can also prove this directly just by writing down the algebra and just playing with the equalities correctly. It's not hard to do. But the intuition is this. Make sense? So I can divide the flow either way I want. Either what's coming out of the sink, so I have a little measuring thing at the sink saying, okay, how much have I used? Or I have another little meter at the source saying how much has come out. Because I don't lose any flow anywhere else in the graph, this is correct. Yes?
Can a flow have more than one source and one sink?
In general, there is no reason not to. What we will often say is that suppose you have multiple sources in a graph and multiple sinks, we will add a new vertex called a supersource that has an edge going to all these sources. We'll have a new vertex called a supersink that has an edge from all these sinks. Any flow in the original graph will be a flow in this graph and vice versa. Like if those sources are producing 10 units of flow each, you just have this source producing 10 times as many sources they are, sending off 10 units of flow to each of them. So it's an equivalent problem. So any statement about flow there can be made here, any statement here can be made there, and so without loss of generality, we can assume we have a single source in the system. That make sense? Yeah. Okay. This is the first notion that that we introduce when we talk about flows. Now, of course, for every notion you have its evil parallel universe version with a beard, and the evil parallel universe version with a beard of flows, not that evil actually, but just a parallel universe version, is called a cut. So let me define to you what a cut is. Before I do that, though, well, actually, let me not do that yet. Let me define the concept. Of course, you've seen cuts already. Right? You've seen mid-cut. You've seen max cut. So now these things, yes.
What happens if you have cycles in the sink source thing?
What happens if you have cycles, even if the graph is a cycle?
Yeah.
Sure. So if the graph is a cycle, remember what I said was the value of a flow is the flow going out of the source minus the flow going into the source. Right? If that net effect is 0, then you have no flow.
Okay.
This is what's called a circulation. Yeah. So electrical circuit, for example, it's always a circulation because you're not producing charge anywhere. The battery is, but the battery counts as kind of part of the circuit as well. So you always think of electrical flow as in loops. Yeah, the ability to have circulation doesn't change anything about the way we define flows. Okay, so you've all seen cuts, and so I'll just recap. We've said that the earlier versions, I think, of cut that we've seen are What have you seen as a version of a cut? Someone define a cut for me. You've seen two kinds of problems related to cuts, right? Min cut and max cut. We're just telling you what a cut is. So I have a graph, etc., etc. What's a cut in the graph?
Covering
It's a separation of two groupings of vertices, and then you remove all the edges between them. Right? Or the edges in the cut between.
And is there a notion of the value of a cut?
Yeah, all the weights of the edges.
That go between the two sets.
That go between the two sets.
Okay? Yeah? So a cut in a graph is basically a partition of the vertex set into two pieces, and then you look at the edges going between them. We've looked at a case where you want to find a cut so that there are very few edges going between them. We've looked at a case where you want to find a cut so there's lots of edges going between them. Right? Let us change that definition just a little bit to be more specific to our setting here. Let me define what I'll call an ST cut. Okay? So an ST cut is a special kind of cut. It's equal to a partition of the vertex set into A comma B as usual, where, and this is the key difference, S belongs to A and T belongs to B. So we want a cut that separates the source and the sink. Okay, that's what we're going to call an ST cut. Okay, so let's go back to our example graph then. Maybe I'll just copy this out for you. So let's okay. Let me remove all these things about the come on. Okay. Okay. So what would be an example? I lost my labels, let me put them back on. In fact, just for future reference. That's not what I wanted, sorry. All right. What would be an example of an ST cut in this term? So, yes?
Just S by itself and all the other verses by themselves.
S by itself, with everything else, would be a cut. So you can imagine a cut somewhat coming across here like this. Right? That's a valid ST cut because it has two parts. One part is S, one part is T. Another cut, for example, could be this. Right? So now you have S, A, C on one side and B, D, T on the other side. You could, for example, have another cut which would be S, B, and D on one side and A, C, T on the other side. This is also a valid cut. All you have to say with your cut is that it has S on one side, T on the other side. You don't care anything. Yes?
You don't care about connections?
No. You don't. Yes? Same.
The same question regarding the direct edges. The same question the Professor was done.
Yeah. So you don't care. That's why I want to give this example. You don't care. All you care about is a partition. That's it. Okay. All right. Once you have the notion of a cut, we'd also like to talk about the value of a cut. And we've already seen that you can count the weight of the edges. But in this setting, I'm going to introduce a new set of numbers that is going to be useful for what we want. The new set of numbers I'm going to add are what I call capacities. So I'm going to introduce something called a capacity, which is also going to be a function from edges to the reals. So let's say, so define the capacity, which is again a function which we'll call C, from the edges to the reals, which is some function of an edge. You should think of a capacity as, how big this road is or how wide this line is. Okay. So then we can say the given an ST cut we'll call it AB, the capacity of the cut, which we'll write as sort of strange notation, right? We'll call it the capacity of the cut, is the obvious thing, is the sum of the capacities of all edges that go between the two sets. So AB is equal to, let's see, sum over all V in A, sum over all W in B of the capacity of the edge. Okay. Yeah.
In this way, we need to maintain that all the vertices from A has a directed edges to vertex of B.
No, you just count the ones that have.
The only few. That means the one which is, let's suppose we have source in one side and we have the earlier one, the S, A and C in one side and the B, D and T in other side.
Yeah.
So only A and C are having the vertices towards B and T, and there is no vertex different.
Yeah,
no
so
edge directly from.
let's go back to that example, right? So here, I haven't put capacities on it, but I could. And in that case, yes, if SAC was my cut, and with BDT, I would be looking at that edge and that edge.
Okay, only the one between.
Yeah, because the thing is that what you're trying to say is, okay, how much, intuitively what you're saying is, what is the maximum amount of water or traffic I can push from S to T? It's a very directed motion. That's not between S and T, it's from S to T. Okay. So the maximum amount is the maximum amount of capacity. Okay. Which brings us to the next point, is that now that I've defined the evil twin of flows as cuts, I will now link these two notions. Yes?
Suppose there is that amount of traffic flowing from S to A. In that case, what would be the that weighted edge is?
I'm going to tell you right now in a second. I'm going to answer that question right. Okay, so hold on. Yeah. So like I said, I want to link these two notions, the notion of a flow and the notion of a cut. Right? And the way I'm going to link them is by a constraint. And I'm going to say is that for all edges in the graph, the flow on an edge is less than equal to the capacity of the edge. Okay? So the extra constraint I'm going to put in my flow now, along with all the other constraints I have, is that I can't push more flow on it than its capacity is letting me do. So the capacity is a function, in some sense, of the graph itself. It's something that's given to you as part of the input to the problem, if you want to think of it that way. Right? It's something to do structurally with the graph. The flow is something you're trying to do with the graph, trying to push things around. And so this connection saying that you can push things around, but there's a limit. You can't arbitrarily push water through these pipes. Yeah, that's sort of great. Okay? Makes it, yes?
So that means that every edge is associated with two separate numbers, the capacitance and the flow.
The capacity.
Capacity.
The capacitance, yeah, was electrical network.
Sorry.
We're not going to yeah. Every edge is associated with the capacity, and once you run the flow, it might be starting to associate with the flow as well. Yes. But initially, as the input, you only have the capacity given to you. So the input to our flow problem will be a directed graph with a specific vertex S, specific vertex T marked out, and capacities for all the edges. That's the extra thing that I didn't mention before. And the flow constraints, for a valid flow, it has to be non-negative, it has to have conservation constraints, it also has to not blow through the pipe. Otherwise you get traffic jams or things. Okay? Now we have two notions in this graph. We have a notion of flow in a graph, and we have a notion of cuts and capacity of cuts. The thing that links them is this very beautiful result. So before I get to that, let me first make an assertion that So so again we have a graph, so we've given a graph G, S, T, and a capacity function. And let F be a valid flow. When I say a valid flow or a feasible flow, I mean it satisfies all the constraints. Okay? And let A comma B be any ST cut. Any cut. So F is any valid flow, AB is any ST cut. Okay? So here's the statement I want to make. For any valid flow in the graph, for any ST cut in the graph, the value of the flow is less than the value of that cut. That make sense? So what I'm saying is, you give me any flow that's feasible. I don't care, just any flow. Think of it again, any traffic pattern. And give me any cut in the graph. Could be the worst cut possible. Maybe there's some case where there's just a single edge connecting two sides in the S1, one's S2. That's my cut. I'm saying that flow cannot be more than that cut. It has to be less than equal. The lecture notes have a proof of this. The proof is actually essentially elementary in the sense that you just take the known relationships between flow and capacity and the known properties of flow and just stack them together and you get a bunch of inequalities and outputs. So it follows directly from the definitions of flow and capacity. But does this make intuitive sense to you? What are we saying? We're saying that, and again with highway networks this might seem like it's something you can relate to, right? If there's any choke point in the network, as represented by a separation of source and sink with a very small capacity cut going between them, that choke point is going to constrain the best flow you can do. It doesn't matter what other nice connectivity there is. If there's some choke point in the network, that's going to constrain everything. You get a question?
Yeah, so is this basically because we're not considering edges that go back from B to A when you do the capacitance?
Yeah, because I could have one edge going forward, a ton of edges going backward. They won't help me. I'm trying to push flow from source to sink.
And so because you're not considering the edges going back, that's why you get this inequality, right? If you did consider them, then they would be equal, correct?
I don't know what that means, if I did consider them.
So if you had all the flow going out from A into B and minus all the flow going back from B to A,
That would be equal to the value of the
that would
flow.
be equal to the value.
Of the flow.
Right.
Yeah. That by definition, again, the same argument for the source applies to any cut as well. Because you don't do anything.
And since you're not subtracting, it has to be bigger.
That's basically the idea. That's the proof right there. That's how the proof works. Okay? This leads to some very interesting corollaries. Since I said F was any flow, and I said AB was any cut, I am allowed to pick for my valid flow the best flow possible. Right? So let F star be the max flow, which means the value of F is maximum. Value of star is maximum. Okay? Then it is also true, since F happens to be a valid flow, that V of F star is less than or equal to this cut. Right? I didn't do anything, I just happened to pick as my valid flow the one that was the best. Now let's pick my min cut. Let's pick the ST cut that has as small a value as possible. So let A star B star be equal to the min ST cut, not the min cut overall, but the min ST cut. Then again this is true. Right? Because I just happen to pick this particular cut. Yes? In other words, what this is saying is a very important fact, is that the maximum flow in a graph, as defined in this way, is always less than or equal to the minimum cut. There is no way that you can push more flow than the smallest, choke point. Now, if you think back to the motivation for this, right? They were talking about trying to destroy supply lines in Eastern Europe, right? If there was a war. What would you want to do? If you want to destroy supply lines, you want to say, where can I bomb roads to cut one side, let's say Moscow on one side from, I don't know, the border with Germany on the other side. Right? What is the minimum amount of bombs or roads I would need to destroy? That's your min cut. And if you didn't do that, and if you looked at the network and you only bomb some of them, you now have a graph where there's some flow. How much flow can they now push through? Well, you look at the cut and what's left, and that's going to tell you how much material can be pushed through. So that's where the motivation for these questions came from originally. Of course, since then we've realized that these things are way more important than that. So the max flow in a graph is always less than or equal to the min cut. And this has consequences for highway network design as well. There are other game theoretic considerations that make things tricky, but if you ignore that, the basic amount of capacity you can push through, if you know there's a certain number of, when Salt Lake is trying to provision more highways or more roads, and they have some sense of how many people are coming to the valley and how many people are driving between downtown and Draper every day, these are considerations you have to take into account. How much flow do I have? How much capacity do I need? Or if you're provisioning, I don't know, network service or any kind of networking service you need, you don't have to worry about it. Yes?
So for finding the min cut, you just look for the smallest capacity edge and then...
Smallest capacity cut. There may be more than one edge in it. Right? Each edge might be quite fat in and of itself, but they might be directed in strange ways so that the cut actually...
Oh, right.
Otherwise, the min cut problem would be easy to solve. Just find the smallest capacity edge and smallest weight edge and you're done. That's not the case.
You can never end up with a negative value, right?
Pardon me?
Like if you had like one large value but a larger value in your cut,
Yeah.
like, you cannot end up with negative values, right? For the
No, the cuts are always positive. You just add up the total capacity.
oh, my bad.
Yeah. Any other questions? Yes.
How many counterexamples to equality?
A counterexample to you mean where it's strictly less than?
Yes.
No. The second part of the statement, which is the way cooler part, is that in fact they're equal. The easy part of the proof is that this is less than equal to, and we've already outlined how this might work. The hard part, or the harder part, is that they are in fact the same. So let me write that down here. And this was first proved by Ford and Fulkerson back in the 50s. And one second. So the main claim, theorem, if you wish, is that in fact the value of the flow is equal to. So they exactly match. And this is a kind of a cool result because on the left-hand side is this weird thing you're doing with putting flow on edges and stuff. On the right-hand side is what looks like a basic structural property of the graph. Right? You have a graph, you have capacities and edges, it's some basic structural property. Right? You just look at the graph and you can find the right-hand value. To get the left-hand value, you have to do some work, but the right-hand value just is. It's a function of the graph itself. So you're saying there's a basic structural property of the graph that limits what you can push through it. And again, it's not surprising, but it's kind of nice that they're actually equal. This doesn't always happen. If some of you, I know a couple of you are in the convex optimization class. For those of you who are, and we'll talk about this later, this statement here is an example of weak duality, and this statement here is an example of strong duality. So, but we'll talk about that in more detail when we talk about your program. That the flows and cuts are essentially duals of each other. 1 second.
Last semester? This is your fourth semester, right? Fifth? Oh, you came in for thesis.
Is that on the website?
But there are no admissions in spring, right? Oh, yeah, I think. Even master's? Yeah, PhD is special. So this semester, got any solve offers yet? It expired? I got it in last year in November. So there's a 6-month deadline to respond. Which company?
Yeah.
So this week
Yeah, so if you write the primal element, first you think it's dual, you get the cut and here. And so since one is maximizing, one is minimizing, you get a struggle
Praxis recently.
Well, I know you did Lagrange dual, and so you do KKT condition. So the KKT conditions of the dual version of what is called slackness conditions.
Yes, slackness, I think we.
You look at primal variables and dual constraints.
Yes.
We're going to see. I won't mention that exact form here, but you will see that happening.
So that slackness we usually use for numerical analysis.
Right.
Analytical.
And what I mean is that here, with every non-zero, so the multiplication of the primal variable and its dual constraint must be 0.
Yeah, exactly.
So if this is non-zero, so if the primal variable is non-zero, this dual must be exactly the stack. And so that we'll see that happening.
Yeah, so today only I can share about we were explaining how this is not very intentional and very careful target.
Right, and so you
like sensitive to
right, in fact you can use a slack value to decide how close to it.
exactly.
So you can actually prove things. So there's a whole framework of approximation algorithm, which I'm not the primal dual approximations. So you look at the primal dual solutions and use them to decide how far away from it.
And use that to your favor, like when you are trying to optimize some powers.
Yes, but a lot of algorithms, they are based on looking at the dual, looking at the slack constraints of the dual, and saying, okay, I need to focus on these constraints, and then doing something and going back to the dual.
They are directly related to that derivative.
Yeah, that's right. And so sometimes if you don't know primal dual theory, you cannot even design these algorithms. Yeah, you have to understand that. Because you can take away the primal dual stuff later, and you can see how the algorithm works. And in fact, you can think of this as a primal dual algorithm.
Yeah.
But you won't know it is, and you won't come up with it. It's very hard to come up with it unless you understand primal dual. That's why I mean that flows are a gateway to sort of bigger discussions of
Yeah, so I was just wondering this, so we don't, so the directions don't,
They do. You measure from S to
when we find the primal,
yes. Yes, there's the A side which contains S. There's the B side and H. The direction is from A to S.
so the value of
Edges from A to B.
always positive.
It's not different. It's just only the edges from A. There's no difference. I'm not surprised.
We are not there are edges from
Because they can affect the flow going to
we
B.
only consider edges which are
Right, but because this is one-way streets, right? If I'm trying to get flow from here to there, I only care about what I get this way. What I do that way is not going to help. In fact, it's only going to reduce my flow.
that's why the value is less than
That.
by the way, the last lecture when you were listening,
Was it?
I didn't actually expect. After that, Contradiction, I
lot of overwhelmed by all these professors because of these small things, nitty-gritties, really helpful. And that's what all the teaching is about. Actually, big things means all this. These small things, because that's where we learn. That's where we learn.
So you want to do so? Okay, so you want to do so.
Exactly.
Okay.
That's I have read a lot of papers, but yes, it's really useful when somebody is starting and this course is already not hard, but like it takes a lot of effort. They are not easy. So when this project comes and you have any idea how to tackle this kind of
So I put the notes on that one, so you can take a look at that. Also, what I will do is that paper I selected yesterday, that's going to be my project. But my deadlines are ahead of your deadlines. So I'm going to submit my one-page version where you want to look at it. So this is what, I'll have to, I'm going to pretend that I don't know what I'm doing. So I will write out a one-page, two-page report saying, hey, if I didn't know the paper,
so that we have a better idea.
and I'll write a full 10-page report in this paper so you can see how that works.
Actually, I want to become an officer, but I'm so trying to manage my life and semester.
Speaking of which. Okay. Let's continue. So the beautiful fact about flows, as I said, is that not only can you upper bound the value of flow by the size of the cut, the min cut in the graph, they are in fact equal. And this is what is called the max flow min cut theorem, for obvious reasons. That the max flow in the graph is equal to its min cut. Of course, I've not proven this yet, right? All I've proven is that, or not really proven, but give you an idea for is why the one side of the inequality holds. Okay? And how, and I'm not asking for the details, but at a high level, right? How might one try to go about proving this, knowing only what we know from here? So what might be a good proof strategy? Not an actual proof, but a way to think about how we are. Yeah?
Contradiction. Proof by contradiction.
No, I know, but in this particular case.
Assume that the maximum flow value can be greater than the min cut.
Okay? But haven't I already, so let's assume this part is true. I don't have to reprove this. What I want to prove is this. So a proof by contradiction would have to instead assume that the flow is strictly less than the min cut. So what Ian was asking, right, is that possible? And I have to show no, that's not possible. There is no way to have a flow, max flow, that is strictly less than the min cut. Right? That's one way to go about doing it. What are other ways you might think about trying to do it? Again, at a high level. So this is an example of a strategy. Right? I don't know how to do it by contradiction, but I can at least think, okay, let me try to do it this way. And that's an example of a strategy. Yeah?
Another way you might try to do it is round it on both sides so that it has to be both greater than equal and less than equal.
Right, so one way to prove that two things are equal is to prove that they're both less than equal to each other. We already have one side. So one way to argue this would be to show that there is a cut whose value is less than equal to some flow value. Right? So you'd have to produce a cut and you'd have to produce a flow so that the flow was greater than or equal to the value of the cut. And that would prove what you wanted. Right? Okay. What else? Anything else to come up with? Yeah?
I'd say that maybe an intuition as to where we might start is that, like, if you were to do a min cut, you might have edges coming back from B to A, but in that min cut, on the maximum flow, those edges coming back would not be advantageous for the max flow.
So they would.
Those would have flow 0.
They would have flow 0.
Yeah.
So you would try to argue that if you look at the min cut, it must have the property that there will be no flow coming in somehow. Problem is that, yeah, okay. Of course, now my min cut itself has no notion of a flow attached to it. So I have somehow, but yes, you're right, and in fact, that's what will happen, that there will be no flow coming in if it's a min cut. Here's another, which is related to all of these ideas, is that, So we want to prove that they're equal, or we want to come up with examples. Suppose I gave you a cut and a flow whose values are equal. So it's along lines of Victor's suggestion. I just give you this value. I say, okay, look at this flow value. It's feasible, and look, its value is equal to the value of this cut. Would that prove my result? Yes or no? I see this and I see this. So I see both things going on. Okay. I can't do the same. Thoughts? So my claim is that I will give you a cut, I will give you a flow, and I will show you the values are equal, and therefore I'm done.
That would work for that one graph.
Sorry, 2 minutes.
Actually, unless it's not naked, because we are going to do that it's naked.
So you're saying unless I prove that this cut was a min cut, this won't work. That's what you're saying?
And for that also we need to check that for all the cuts it's valid.
Okay. Any other thoughts on this? Yeah?
Can we prove it because you've just shown that for a particular input that this is true, but not for all?
I've just shown you for a particular input, it's true, but not for all.
So I feel like you don't know anything about the flow, right? So it could,
I don't know anything about anything right now. Yeah.
it could just be some random flow that's not maximal.
Right, but it's feasible. All I'm telling you is feasible.
So what I'm saying is if you give me a flow and a cut that have equal values, that may or may not be a max flow and cut pair. It may not.
It may not be. Right.
If you construct a flow and a cut that are equal, then that flow has to be the max flow.
Why?
Because if that is not the max flow, then you have a higher flow. But we already know the other flow has to less than all the possible cuts.
Okay.
Therefore, that's
Very good. So his argument is that, if I'm saying this correctly, you're saying if I was able to produce a flow and a cut that are the same value, this has to be the max flow. Because otherwise, so the flow cut, there's a flow that's bigger, but wait a second, I just said every flow is less than every cut. This can't happen. So this had to be done. Is that what you're saying?
yes.
Any thoughts on that?
I agree with that, and likewise, you could say if this wasn't the min cut, then, there would be...
If the cut is lower, that's not possible either.
Yeah.
So in fact, while you all are correct that you can't just take any flow and any cut, in this particular case, because I have this given to me already, I actually can do that. I can produce any flow that's feasible, any cut that's a valid ST cut, and if their values are equal, I'm done. Yes?
If there is no flow, flowing through this to set, then it's obviously
Sorry?
if there is no flow if there is no flow which is possible in this case, like if you take a minimum cut, so that would be a valid minimum cut. Go through the network, go through the network.
You mean if there's nothing at all, the network is disconnected,
Yes, there would be a minimum cut.
and that cut value will be what? No, but what did that...
value which can...
No, but let's say I had a network that was disconnected. There was no way to get from S to T in the graph. What's the value of the cut?
There's no way to get from it.
No, the answer is 0, right? What's the value of the flow? 0. So it still works in that case, right? So in fact, because we have already shown the statement above there, which maybe you can't see it, okay, that statement above there, all we need to do, famous last words, all we need to do is produce a flow and a cut that have the same value. Okay? And that's what I'm going to show you. Yes?
So I'm actually a little confused. So if you have a graph that's just S and T connected by one edge,
Yeah.
it's capacity 1, right?
So, you decided that one is capacity 1. Okay, good.
Yeah, so the cut that separates this is exactly 1.
Yes.
Has a weight of 1. But I can take a flow that has value 0.5, for example.
Sure.
It's not maximal.
Sure.
And it's less than this.
Sure. That's why we have that statement up there, right?
So what are you trying to do with this? I give you some flow, I give you some cut.
So you're not doing what I wanted. I want a flow and a cut that are equal in value, not one where it's less than. Are you saying this is somewhat too easy? Is that what you're concerned about?
I guess I'm not entirely convinced that coming up with any random flow and any random cut that happen to be equal will necessarily improve what you want to prove.
Okay, let me prove it then.
Perhaps-
No, let me prove it. So let me prove the meta result that if I could do this, then it would be correct. Okay? So if I were able, so suppose there exists some flow that's feasible and some cut that's a valid ST cut such that V of F is equal to, right? Then I claim that is maximum and A comma B is minimum. That's my claim. Okay? And of course I have to do this for every possible graph. Right? For any graph I should be able to do this. Any instance. And then I've done this. So why is this claim true? Well, the claim is true is that we know that, so let's say, suppose F star is not equal to F. So the actual max flow is something different. So then we know that V of F star is greater than V of F. But that's equal to the cut A comma B by definition. And this is a contradiction. I have a flow that's more than the cut. So that's not possible. And then the same thing the other way around. Suppose there was a cut that was smaller, I would get a contradiction.
So what you said here is that the value of the optimal flow is greater than the
No. Suppose my flow was not optimal. Therefore, there's some other flow that is optimal, but then I would get a contradiction.
So if you look up at the inequality above
Yeah.
on the previous page,
Yeah.
so this is less than or equal to the minimum cut.
No, but look what I said here. Look at this inequality.
Oh, okay.
Any flow is less than the value of any cut. That's the property I'm using. Sorry, I was pointing the wrong inequality, but what I'm using is that property. So you're correct. I need this stronger fact, not this weaker fact. Yeah. Okay. All right. So how are we going to do this? How are we going to actually produce this? We're going to do this as Ford and Fulkerson did, by constructing an algorithm to produce a flow, and then proving that that flow in fact matches the value of a cut. Okay? And this is what is known as a Ford-Fulkerson algorithm. Okay? And to do that, I need to introduce a bit of notation. So let's go back to our graph again. Okay. Okay. So let's now put some capacities on these things. Okay. So let's say this is going to be I want to use the numbers from the notes, which I don't really. I guess I could, just to make sure it's consistent. So let me just see if I can get hold of the notes. Okay. So these are the capacities. Okay. So first of all, what is the min cut in this graph? So I'll look at it right now. So what do you think is the min cut? So the red numbers are the capacities. And if you do have a value, tell me the cut that gives you that value. Oh, sorry, I have to label one edge. One vertex is unlabeled. Let me just label that first. Okay, now tell me. So what is, if you take S as your cut, which you can, what is the capacity of that cut? What is the collection of edges coming out of that cut? Well, 20 plus 10, 30. right? There are two edges coming out of the source. Their total capacity is 30. So that's the capacity. So your min cut has to be, if you're going to give me an answer, it better be less than 30. Otherwise, that's already an answer. Yes?
25, S and A.
S and A. So if you look at S and A, the edge S to C is coming out of the cut. The edge A to C is coming out of the cut. The edge A to B is coming out of the cut. And that has total value 25. Okay? Can we do any better?
SAC.
SAC. So walk me through the end. Okay, so SAC, what are the edges coming out of the cut?
A to B and C to D.
How much is that cut value?
5 and 10, so it's 15.
It's 15. You don't count the edge going back. So this has 15. Can you do any better? Yes?
I have actually a different question.
Yes.
So can you explain, does this not follow the conservation principle?
These are capacities, not flows.
Okay.
These are just capacities. These are maximum values of the amount of flow you can push in any edge. Think of these as the diameter of the pipes. So they don't have to satisfy any constraints, as long as they're non-zero. So flows that will have to satisfy those constraints. Okay, so we have 15 candidates. Anything better? Remember, you have to have S in one side, you have to have T in the other side. Can you get a 10? I mean, clearly these are very multiples of 5. Is there any way to get a 10 out here?
Have at least two edges.
Yeah. Okay, so as far as we can tell, the min cut here, the min ST cut, not the min cut, the min ST cut. By the way, if I can compute the min ST cut in a graph, can I compute the min cut? Suppose I have a black box that for given a graph with S and T will compute the min ST cut. Can I compute the min cut?
Repeat it and find it.
Sorry?
Repeat it 20 times, find it.
How many times you repeat it? 5? 23? 17?
Squared.
Huh?
N squared.
Who said n squared? Why?
Pick every possible vertex as S and every T.
There you go. Easy enough. Take every pair and then one of them's going to be the one. That's right. Okay, anyway, it's a digression. So we have the min ST cut, that's 15. And now we want to find a flow, which hopefully we'll find will be in fact 15. And so this is how the Ford-Fulkerson algorithm works. You can think of it as either a greedy strategy or not. It's up to you. The idea is that find a path. So think of sending little, car sensors down this highway to sort of check and see whether there's a path. So if there's no jam on the highway, you should be able to get a car to go from S to T, right? So look at this graph. Can I send a car from S to T?
Yes.
Tell me a way to send it. Any way you want.
SABT.
So one proposal is SABT. Okay? How many cars can I send? Like if these are numbers of cars, but how many cars could I send from S to T? Along that path. I can send 5 cars from S to T along that path because the capacity of edge AB is 5. The capacity of edge SA is 20. BT is 15. The choke point along that path is 5, so I send 5 cars along that path. Okay? Alright. What do I do next? Now I can't send any more cars along the AB. What can I do now? Is there another way to send cars from S to T? You can go SCDT. And how many cars can you send? 10. Why? Because the minimum capacity of an edge along that path is 10. So you can send 10. How many cars do I send total? 15. Hey look, the min cut is 15. In this graph at least I've shown the answer. Of course life is never going to be that easy. But the algorithm is the same. The Ford-Fulkerson algorithm is basically this. So this path we constructed is what we'll call an augmenting path. It augments the flow. Okay? So the Ford-Fulkerson algorithm basically says, while That's it. Not a good path, not a bad path, not a short one, not a fat one, whatever. Just as long as there's some path, do it. And that would be fine, except you could make a mistake. Since I'm not telling you how to find a path, I'm just saying find any old path. You could end up making a mistake and choosing a path that causes you trouble. Is there a way to do that? S, A, B, C, D, T. So the minimum capacity along that path is 5. I would push 5. Why is that a problem now?
Because when you try to go through CD again, it only has 5 more that you can push through.
Ooh, is that so?
Because
Yes, okay, let's draw this out. So let's draw this out. So let's do 2 paths. So let's augment. So path 1 we're going to. So actually let's copy this guy. Okay, so let's mark this first path in, I don't know if you can see this green. Let's try anyway. So the first path proposed is going to be along here, here, and here. Okay? So the path is S, A, B, C, D, T, and the flow value is 5. Okay? The next path we're going to pick is, now we can no longer go along AB, so there's no point going to A, so we go along SC. CD already has 5 units of flow on it. There's only 5 more to send. So if we go at 10, 5, 20, we can only send 5. So we go this, we go this, and we go this, right? And this path is and now if I want to just, not change these paths, I'm stuck because CD is full, AB is full, right? But I only have 10 units of flow. So something went wrong in my Ford-Fulkerson algorithm because I didn't actually change any of the paths that I already had. So the part that I did not tell you is that after every time you augment, you have to change the graph. And this is where the magic of flow comes in. This is what makes flow different to, say, a greedy strategy or something else. In a greedy algorithm, you make a decision. You don't revoke your decision. In a flow algorithm, there's a systematic way to change your mind about your decisions without doing a full backtracking, which could be horribly expensive. One second. And it rests on the idea that flow is fungible. Water is water, cars are cars. If a car happens to go this way and that way, it could also go this way and this way. Or, in other words, I could have, in this case, right, I have flow coming in from S to C on the blue line. I have flow coming in on the green line. But when they come out, I don't know which was green, which was blue. It's just all flow. And I can exploit that fact. You had a question?
Yeah, on vertex C, isn't the flow length greater than the flow going out?
Well, there is 5 units of green flow coming in and 5 going out. There is 5 units of blue flow coming in and 5 going out.
Ah, okay.
In fact, if you notice, the way I push flow from S to T, it is guaranteed to satisfy the conservation constraint because I never take out more from a vertex than what I push into it. I just take the same amount along a path. So it's trivial to see that this kind of augmenting path construction is going to preserve the flow, the conservation constraints on a vertex. You have to be careful with the capacity constraints, but the conservation constraints are satisfied. Right? Yes?
Just curious, if we go from D to B and to T, that's still valid, right?
Sorry, say it again. Where do I go?
So S, A, B, C, D.
This is in the green or the blue?
Green.
The green is S, A, B, C, D, T.
Yeah. If we can go even D to B and then B to T. So it will be a cycle in the path.
You could.
That's a valid path.
That's a valid path. As long as, yeah. And you might say, oh look, the cycle, why bother? Just go straight from B to T, which should have been the original one. And that's in fact part of how this thing works. But there's nothing, this is a valid path. Yeah. Okay? So there's a problem here. And the problem is going to be resolved by modifying the graph in a subtle way after every step to allow for the possibility of changing your mind. And here's what we do. What we do is we construct what is called a residual graph. So let me explain what that is. Let's look at a single edge. So we have some vertex V, and we have some vertex W. And let's assume that in our graph, all edges go either from one direction to the other, but not both. You don't have two edges going both ways. This is easy to arrange. Again, the notes discuss how you would fix that. But let's assume we have an edge going from V to W. This is a real edge. And it has some capacity C. Okay? Now I push some flow on this edge. Effectively now, if I want to pretend that I have a new graph, right, where I didn't know this flow had happened, what is the residual capacity, the leftover capacity I have? So I push flow F through this edge. How much capacity do I have left? C minus F, right? So if I had to draw this edge again, right, in a new world where I didn't know the flow had been pushed, but it's there, the residual capacity on this edge would be C minus F, right? But there's one more variant, and that's what we've been using so far, right? We basically, in the previous example, we said, oh, wait a second, the capacity on C to D has gone down from 10 to 5 because of the green flow. We only have 5 left to push, and that's why we can only push 5 here. But there's one more thing you can do. You can change your mind. What does that mean? Let's go back to this edge again. I pushed F units of flow from V to W. Suppose I want to change my mind and not actually push F and push less than F. How much can I change my mind? I can change my mind to the tune of F units of flow. And you can think of changing your mind as pushing flow backwards. It's like, no, stop. You were sending 6 cars with me, I'm sending 2 of those cars back. I changed my mind about how the routing has to go. In effect, your initial edge has become a new edge that now looks like this, with the capacity of F. So this is a very, very important step we're doing here. What we're saying is that when I push F units of flow along the edge VW, and that direction is important, I have reduced its capacity by F, which is obvious, but I've also given myself the chance to change my mind backwards to a maximum amount of F by pushing flow back, or by not pushing that much flow. So I have F units going back. If I now imagine running a flow procedure in this new graph, that flow procedure, not knowing where this edge came from, might decide to go on it. That effectively amounts to letting the flow algorithm change its mind in this very clever way. Okay. Notice that the sum of the forward capacity and the backward capacity is always going to be C. In the beginning, the forward capacity was C, the backward capacity was 0. C plus 0. Forward capacity goes on to C minus F, the backward capacity becomes F. And you can convince yourself that as I can do these updates. So what happens when I do an update? If I now take this edge and push flow F through it, F prime through it, what's going to happen? So this was an edge, this was a flow of F, right? And I now push, so now I say push F prime from W to V. What's going to happen? Just the same way as before, the capacity of the WV edge goes down by F, right? So if I do VW again, the capacity of the VW edge goes down by F, which means what? Its capacity becomes F minus F prime. The capacity of the back edge, which is the original, E minus F plus F prime. And effectively, if you look at this, what has happened? What's happened is that we have changed our mind about the amount of flow we want to push through this edge. We've reduced it from F to F minus F prime. Okay? So there are two things I want to convince you of. First of all, that these transformations are legal, they preserve the flow and they preserve the validity of the flow, and that should be clear to see. But secondly, that you essentially have created this memoryless property. That once I run a single augmenting path, I can transform the graph so that it's as if I have a brand new graph. But it still has information about what flow happened before. So the Ford-Fulkerson algorithm, this is called the residual, so this is called the original graph, and this is called the residual graph. So for every edge that you push a flow on, you modify it in this form. And so the Ford-Fulkerson algorithm, which I showed you before as this, while a augmenting path exists from S to T augment, is really this. Exists. While an augmenting path exists in the residual graph, augment okay? So let's do this. So let's take our graph here. Okay, which I think I have a paste for. No. Okay. Let us now run that bad, so we had an example where we got the right flow just by doing things cleverly. Let's run the bad flow and see what happens. Okay? So remember the paths in the bad flow were S, A, B, C, D, T. Right? So what's going to happen is, and I'm going to put the new edges in blue. Right? When I push a flow of 5 from S to A, I'm going to get a new edge going backwards, which has a capacity of 5, right? And I'm going to have a new edge going here, which has a capacity of 5. A new edge going here, let's see, which is 5, 5. Is this correct? Yeah? And now these capacities, of course, will become, this will become what? 15? 15, this will become 0, this will become 10, this will become 5, and this will become 15. Right? This is what our graph now looks like after the residual updates. Does this make sense? Remember what I said to each edge? You give a back edge with the amount of flow you push through it. Now we put in the next one, and I should have used green for this because blue was for that one, and I flipped them around. So, but let me do the next one anyway. No, just to confuse things, I'll do that one in green. So now I can see that if I want to push along the S to T, I'm going to have flow of 5 here. So this is going to be a back edge, which is hard to see, unfortunately. You know what? Okay, let me just. Better. 5, and this one is going to have again a back edge of 5, so we'll make this one 10. Okay, this is again going to have a back edge of 5, so we'll make this 10. Right? This capacity, so let me go back to red. This capacity goes down to 5, this goes to 0, and this goes to 10. Okay, now I have this horrible mess of a graph here. But in this graph, is there a path from S to T?
Yes.
There is? Oh, I didn't know that. Okay, tell me the path.
S, C, E, T.
S, C, B, T. Notice now this new path is not stuck because of this residual construction we did. We have this back edge we can now use, which effectively boils down to changing our mind. So we go S, we go forward 5, we go forward 5, and we go forward 5 there. And that's a valid flow. Right? So what that's going to do, so we're going to go forward 5 here, so this becomes 0. We're going to go forward 5 this way, which sends this back to 15. Okay? And this becomes 0. And we go forward 5 here, which sends us to 10. We get a flow of 5. How much flow do we now have? We have 15 flow. But if we stand back and look at the flow and rethink about what the flow looks like, what does it look like? It looks like a flow of 5, 5, 5. Sorry. No, is that right? Yeah, a flow of 5, 5, 5 that way, and a flow of 10, 10, 10 that way. So essentially, even though we made bad choices and got stuck in a bad situation, we were able to get ourselves out of it, effectively getting us back to the correct flow that we had designed earlier. Because of the construction of this residual group. Which again, I will remind you, looks like this. Oh, sorry, I ran out of time. Okay. Next week we will talk about how to prove. This is not enough, it's an algorithm. We will talk about how to prove this algorithm in fact uses the optimal max flow by constructing a cut that matches that value. Okay, sorry, I didn't let it run out of time.